what I do want to talk about right now and kind of get into in a little bit more in depth is the topic of what's called the Generalized Logistic equation. Or the Generalized Verhulst equation. And show that we can solve the Generalized Logistic equation using the linear theory that we talked about before, even though the differential equation is a nonlinear equation. We talked about before the logistic equation model, which the dimensional form of the model was the assumption that the rate of change of population was equal to the rate, some rate constant r, times the population at time t, times 1 minus the population over the maximum population. Okay, and when we did our non-dimensionalization here, to translate, we did p is equal to y times m, and we did tau is equal to r times t. So we introduced these new variables, and when we non-dimensionalize, the differential equation that we got was dy d tau is equal to y times 1 minus y. And this is good for a constant rate and a constant maximum population, but the question that you can ask, which is generally a very valid question, is what if the rate r or the max population m are not constant? And depend on time. How to deal with this scenario? This means that this differential equation, which is a nonlinear autonomous differential equation, will now become a non-autonomous nonlinear differential equation. Is r of t be a function of time, some function of time that we have to determine, multiplied by 1 minus p over m of t. And you could ask, how do we go through and solve this differential equation? Well, the first thing we'll do is we'll simplify this a little bit. Write this as distribute r of t through, so you get r of t minus r of t over m of t times p times p. And because r of t and m of t are now non-constant, they're functions of time, we have to be very, very careful with this. We have to be careful with how we non-dimensionalize. So typically, for a typical problem like this, we'll have some characteristic population, we'll call it capital K, and we'll just choose to non-dimensionalize by this capital K. Could be the maximum of the function m of t, so the largest possible value of m of t. It could be a number of different things, but again, we'll just non-dimensionalize. We have to choose some k which is a characteristic population value. Sometimes called it's related to the units and the fundamental length or fundamental population size of the problem. And we'll also non-dimensionalize t by introducing a new variable tau, much the same way as before, and we'll call this t over capital T, where t is the fundamental time scale involved in the problem. Before, our 1 over t was the r, the constant rate. But in general, if r of t is variable and m of t is variable, we'll have to choose a different value for our fundamental time scale as well. So when we non-dimensionalize, this differential equation then becomes the t derivative of any function, specifically of p here, is the derivative of p with respect to tau multiplied by the derivative of tau with respect to t from the chain rule, and the derivative of tau with respect to t is 1 over capital T. So when we plug in our non-dimensionalized variables into this equation, we end up getting, it'll be, well, p is y times k, so you'll get k over t times dy d tau is equal to r of t, which is r of tau times t minus r of t, which is r of tau times t over m of tau times t times p which is k times y times all of this times p again, which is k times y. And we can divide by k here, divide through by t to finally get the following differential equation, where I'll write it down first. We'll call this function right here, when I multiply by t, lowercase p of tau minus q of tau times y times y. And this is the generalized, or the non-dimensionalized generalized logistic equation. Or generalized variables, OD. This is where p of tau, really want to emphasize here, this is a lowercase p of tau is the function t times r of tau times t, and q of tau is the function negative for positive r of t, the r of tau times t times k times t over m of tau times t. And the question now is, how can we go through and solve this equation? And it turns out there's a little bit of a trick that we can do here, and it's a trick that we'll see is actually relatively common even for nonlinear systems. And this differential equation, as written right here, is in fact a linear, or sorry, non-linear. It's a non-linear ordinary differential equation. But the idea is that, well, we know how to solve systems of single linear first order ordinary differential equations using the variation of constants formula that we talked about before. So what we're going to do is, well, is there a way of turning this nonlinear first order ODE into a linear first order ODE. And this is what we're going to do. We can do this, and it's really quite amazing. So to solve this equation, we introduce the new variable x, or x of tau. It's a function of tau. And x of tau is defined as being 1 over y of tau. Now we can only do this if y is non-zero, so you got to be careful about plugging in this assumption. But as long as this is satisfied, then x is going to satisfy, or the derivative of x prime of tau, satisfies the following. It's going to be, from the chain rule, 1 over y of tau squared times negative 1, all of this multiplied by the derivative of y prime of tau. And I'm going to remove the functional notation for short right here, just because it's going to be a little bit easier to see the manipulations that we're going to do. But remember that x is a function of tau here, and these derivatives are all tau derivatives. This is from the chain rule, and therefore if we use that y has to satisfy our differential equation, this is equivalent to saying that negative y prime is p of tau minus q of tau times y over y squared which is the same thing as x prime is equal to negative p of tau times 1 over y plus q of tau, because y times y is y squared over y squared is 1. And then the last thing to do here is to note that x is defined as 1 over y. So you have x prime is equal to negative p of tau times x plus q of tau. And this is a new differential equation. It involves our functions p and our functions q. This is a new differential equation. Linear, first order, ODE, that is equivalent to our original, or the y ODE, even though it's much simpler to solve. We actually have a nice expression to solve this. And it's really important to point out that this example illustrates that we can sometimes transform a nonlinear problem into a linear problem through some suitable transformation. This is a really, really big idea, and it's not always easy to see what transformation to use. But when we can do this, it's a very, very powerful technique towards solving our differential equation. Because now we can solve this. Right, we have that nice formula from our previous lecture that essentially gives us directly, under certain suitable conditions, a direct formula for x of tau. It's going to be x naught times e to the negative, this is negative p of t, so when you apply that formula, remember that it's the e to the negative integral from tau naught to tau of the function p, is this definite integral, plus e to the negative integral from tau naught to tau of p multiplied by the integral from tau naught to tau of e to the positive tau naught to s of p of psi d psi. And it's the integral of this function of s times q of s ds. And it's more convenient for this application, I think, to express this as a fraction. So I'm going to go ahead and do that right here. So it's going to be this fraction, and we'll have to move this down a little bit. Because you have e to the negative this integral plus e to the negative this integral times this. So if we factor this out and re-express this as 1 over e to the positive this integral, it's going to look a little bit nicer here. This will be x naught plus then this entire expression right here. I think I'll make this a little bit smaller. This integral sign right here, just to make sure stuff fits really nicely. And same thing right here. But this is really quite incredible that we were able to do this. And now that we have this nice solution for x, which is a general solution to this variable coefficient first order ODE from the variation of constants formula, we can actually go through and directly get our solution for y. Because we know that x is 1 over y. So the exact solution for y is going to be 1 over our previous solution. Or 1 over this, which is going to be, well, essentially this same expression right here, but 1 over it. So this in the numerator and this in the denominator. And we also want to re-express x naught here as 1 over y naught. Which we can simplify a little bit more by bringing the two terms in the denominator to a common denominator. So you'll have, this is going to be 1 plus y naught times this right here. Oops, I just realized I need to delete this term right here. I apologize for that. I divided, or I factored this out right here and divided by it, but I didn't delete it from right here in the numerator. I apologize for that overlook right there. But that's actually pretty nice because it makes things look a little bit nicer here when we go through and write this down. I'll put parentheses around all of this just to indicate that it's this entire thing divided by this thing right here. And that also simplifies this down here as well. And if we bring the denominator to common denominator, we have to also multiply the numerator by y naught. But there you have it. This is our solution for y of tau. So this is great. This gives us the non-dimensionalized solution, the solution to non-dimensionalized, or the non-dimensional generalized logistic first order ODE. And you might be asking, well, how do we kind of convert this back to the dimensionalized form so we can, use it for specific examples? And the answer to that question is much as we did before. So we know that y of tau is the same thing as p over m, or p over k, because k is our characteristic population scaling factor. And so this is much a process of just going through and using what we know about how we've scaled and solved for why not, as well as this p and q function. So y naught is p over k. So p naught over k, and y naught here is p naught over k. And then remember that lowercase p and q are these functions of our chosen scaling parameters. So this integral of p of xi d xi, where xi is the variable of integration for tau, so this is the same thing as r of xi t d xi, and it's the same thing right here as well. P of xi is r of xi t times t. Oops, I forgot that t up here, so I'll put that in right here. Times t d xi, and this q of s, again, s is an integration variable for tau, representing the integral of q of tau. So it's q of, q of s is r of s times t over m of s times t times kt ds. And this is where a little bit of the dimensionalization magic works its way in. This 1 over k here cancels with this 1 over k right here, and this 1 over k right here cancels with this 1 over k, or this positive k right here, because this is on the left hand side of the equation, this is the right hand side of the equation, and you have 1 over k times k. Furthermore, think about how to simplify the integrals. Well, we just want to think of doing a u substitution for both the integral of r of xi t times t d xi, and this s integral right here as well. So we'll do the u substitution. U is equal to t times xi, and the v substitution of v is equal to t times s, to give us that du is equal to t d psi, and dv is equal to t ds. And the bounds also change as well, because if I'm going, right, when xi, say, is equal to tau naught, then u is equal to t naught, and so on and so forth. So really what this simplifies down to is just that p of t is equal to this entire thing, but simplified after we do the u substitution. Specifically, this integral becomes the integral of r of t, r of u du, from t naught to t, as does this integral right here. This is now from t naught to s, to v. This outer integral is from t naught to t. This lower integral is the integral of r of t over m of t, or sorry, r of v over m of v dv. Where this is now the dimensionalized, or the dimensional form of our solution. But it's a nice compact expression. And it's very, very, very important to understand this method, because this is going to be a relatively nice and common way of dealing with general nonlinear ordinary differential equations. There's no set rule or set method to deal with a general nonlinear differential equation, but very often there are many examples where we can, using a suitable transform, transform our nonlinear differential equation into a linear one and use linear methods. But this is a very, very, very powerful example, I think, showing this technique. The form of the transformation might be, in general, is very different from problem to problem, but I think it's a very, very cool technique.